Welcome to P. Calc, Practical Calculus for the Busy Math Student. And in this video we're going to take a look at the simple power rule used in conjunction with rational exponents. Here's an example of an antiderivative that can be integrated using the basic integration rules. The main one being the simple power rule. Whenever we have the integral of x to a power with respect to x, so integral of x to the nth power dx is equal to x to the n plus 1. We add 1 when we run the derivative backwards this way in the integral. And then to keep the coefficient correct, we divide by that n plus 1. And then we have to make sure to include the plus c, which we call the arbitrary constant, because the derivative of a number is 0, so when you run a derivative backwards, there's no way of knowing what number could be there. So we kind of fill the spot with that dummy constant, and we usually use the letter C, capital C, to represent that. Now the simple power rule works for all exponents except 1. The only time it does not work is -1, because if you look at the formula, it means that we would be dividing by 0. So that means that the power rule works for all other exponents, whether they're positive, negative, integer, or rational. And so it's just a matter of, can we express our function as a variable to a power. And then we combine that with a few other important basic rules. We have the constant rule. The integral of a constant dx is the constant times x plus c. Basically just a special case of the power rule where your integral is kx to the 0, if you want to think of it that way. And then because we're doing antiderivatives here, that's what the integration symbol means, we have two rules that are consistent with rules for derivatives. One is the constant multiple rule. It says I can take the constant in or out of the integral, the constant factor. And then the sum and difference rule states ultimately, when you put them together, that you can integrate terms independently. And sometimes, if you wish, we can rewrite it as two distinct integrals. A lot of times maybe we don't have to do that. It's kind of a matter of what's easier at that stage of the game. So we'll be using a few of those here, but the first key step is the rewrite. Just like with derivatives, we don't do derivatives in radical form. It's all based on exponents. Same with antiderivatives, or what are called indefinite integrals. Before we get going, there's a little bit of vocabulary you might want to refresh your memory with here. When we refer to the integrand function is what we're taking the antiderivative of. And we need this differential at the end. Here we see that it's called dt because our function is a function of t on the integrand. And then the integration symbol itself, this s is what it is, a large kind of stretched out s figure, represents the fact that we're going to take the antiderivative. So you're going to practice the notation and make sure you're writing everything correctly as you're setting up these problems. So as we go to do the problem, we have to understand that, well, I don't want the radicals there, and I have to remember that the square root of t to the 5th is t to the 5/2 power. So this is 21t to the 5/2. And then an integral without the differential really doesn't mean anything. And depending where you are in your integration career, I mean, sometimes that differential doesn't feel like it's doing a whole lot, but get in the habit of writing it there. It's important, and without it, your integral really doesn't mean anything. And it becomes apparent the more you learn about integration that really is a factor and very important in the whole process here. So my second term then is going to be 6t to the negative 5/2. Again, we have a differential of dt there. And I've divided it into the two different integrals with the sum and difference rule. So we did a little rewrite, and we applied the sum and difference rule there to state this as two distinct integrals. Now, I'm going to also use the constant multiple rule here. This is optional, but if you wish, the one thing that you can take out of an integral is a constant multiple factor. So I could take the 21 out of the first integral and the 6 out of the second if I wish. So let's do one more rewrite. So it gives me 21 times the integral of t to the 5/2 dt plus 6 times the integral of t to the negative 5/2 dt. So now we're just going to apply the simple power rule. The key here is we have rational exponents. And you just want to be careful with your arithmetic when you're dealing with rational exponents. If we just follow the formula, what it's going to look like is t to the n plus 1. So I have t to the 5 halves. So if I add 1 to that, that's t to the 7 halves. And then whatever that new exponent is, that's what we divide by. So it's divided by 7 halves. Typically, we would put an arbitrary constant plus c here, but when you have multiple integrals, they all get combined. So just remember to put that at the end of the whole antiderivative when we're done here. So we'll keep going. And we have 6 times the antiderivative of t to the negative 5 halves. So now I have to be really careful. It's a negative rational exponent. So n plus 1 here is t to the negative 3 halves is my exponent, divided by negative 3 halves. And then we can tack on our arbitrary constant at the end. Now, this looks a little awkward. When you have rational exponents and you start to apply the power rule, you're building, by definition, you're building compound fractions. And nobody really wants to look at that as their final answer. So with a little bit of practice, what you do when you have rational exponents is you raise your exponent to the n plus 1, and then instead of dividing by n plus 1, we multiply by the reciprocal. So here I want to write this as 2/7 t to the 7 halves. And then in a similar way, we want to write this as negative 2/3 t to the negative 3 halves. So you should get in the habit of doing it that way with the rational exponents, because most people do not want to look at a big ugly compound fraction as their final answer. And like everything else in math, I mean, if you practice and you understand your rules, a lot of times we could jump from our original integral straight to here, straight to our antiderivative, if we understand the sum and difference rule and the constant multiple rule and everything else are in play here. So our final step is to simplify here. So 21 times 2 over 7 is 6. So we have 6t to the 7 halves. And then we have negative 2/3 times 6, so minus 4t to the negative 3 halves with the big plus c on the end. So that's our antiderivative. We call that the general form of the antiderivative. We have the plus c on the end, because basically what we're saying is there are infinitely many antiderivatives, but they all just differ by that constant term, which at the moment we don't know. But for the fundamentals of antiderivatives, that's as far as we need to take it for now. And it's a nice example of the basic rules of integration, but in the special case of the rational exponents. It's the same rules, you just want to be a little more careful. And the key step, I think, is, instead of dividing by n plus 1 here, we end up multiplying by the reciprocal of that new exponent in our antiderivative. If you would like to learn more about integration or calculus in general, you can find more information on my textbooks available on Amazon for a really nice price. Don't forget to subscribe to the channel if you liked it. And until next time, I'm P. Clark.